All right, here's a question that asks you to figure out what the value of the equilibrium constant is. And so this is going to be maybe one of your first practice problems where you incorporate something we call an ICE table. It's just a method that we're going to use to help keep track of some values. You'll see how we use it here in just a second. Now it's saying I'm going to put this number of moles of HBr, I'm going to put it in a 4-liter container. I'm going to decompose it according to the following equilibrium. When the equilibrium is established, I'm telling you exactly what the concentration of Br2 is. We'll use that in a second. So let's start off first with writing down the equilibrium expression. And don't forget, so that's going to be concentration of products raised to their stoichiometric coefficient divided by the concentration of the reactants raised to their stoichiometric coefficient. So here we go, Br2 times H2 divided by HBr squared. Okay, so how do I do that? Let me write down this reaction, just so I have a little bit of space here to deal with it. Okay, and now I want to set up something called an ICE table. An ICE table is a way to deal with the initial concentration of the species in the equilibrium. Think about how the concentration changes. So I for initial, C for change, and then to use those two things to come up with an expression for what the equilibrium concentration will be in terms of the initial concentration and the change in the initial concentration. So you'll see here in a second how we deal with that. All right, so I know that I need to figure out the initial value of HBr, but I know that the initial value of the products is going to be 0. So let's use the information in the problem to calculate the initial concentration. 2 moles divided by 4 liters gets me 0.500 molar. So the initial concentration is 0.500. Now, how is the concentration going to change? Well, the concentration of HBr is going to go down. It's a negative sign. It's going to go down by some value, and we don't know what the value is, so let's call it X. Now, we want the change to be relatable in terms of the same variable X for each one of the different species involved in the equilibrium. So for HBr, for H2, and Br2. So we need to make sure that we consider it with the stoichiometric coefficients. So if I want to use X, then I have to bring in the stoichiometric coefficient. So it's going to go down by an amount X, but it's going to be 2X because of the stoichiometric coefficient. Now I can say that H2 will go up by 1X and Br2 will go up by 1X. Now I have a single variable to deal with in this expression. So how do I deal with the equilibrium concentrations themselves? Well, if I start out with 0.5, that's the initial, and I know that it's going to change by a value of negative 2X, then the concentration at equilibrium is the sum of the initial and the change. So 0.500 minus 2X. 0 plus X is just X, and 0 plus X is just X. And so now I have a way to deal with the entire equilibrium expression in terms of a single variable. So I can write that it's X times X over 0.500 minus 2X quantity squared. Okay, so in a lot of problems, you're going to have to deal, now that you've got this far, you're going to have to figure something out. Now, in some problems, I'll actually give you the equilibrium constant. In this problem, I give you something else. I give you the value of X. I'm telling you that the concentration of Br2 is 0.0955. So then that must mean that X is that number. And if X is that number, then the concentration of H2 is also 0.0955. And I know what to plug in here in the denominator as well for HBr. And so let's do that. So I'll get 0.0955. I'm going to go ahead and square it since I'm multiplying it by itself in the equilibrium expression, X times X. And let's write out the rest of it. 0.500 minus 2 times 0.955, all of that squared. Okay, so I'm going to run that all through my calculator, and I'm going to get 0.0955. I know that seems weird. It's just coincidental. It is the same number. Put it in your calculator if you don't believe me. It actually works out to be 0.9548. So we round to 3 sig figs, we get 0.0955. And so that is the concentration, or that is the equilibrium constant in terms of concentration. And that's what the problem is asking for.